Hello and welcome back. In this video we want to use clustering to analyze our nanoindentation data. Previously we have looked at a dual phase steel sample in the electron microscope and noticed that there are some artifacts that we also need to remember in our analysis and placed a grid of nanoindentation onto our sample. Looking at 5 kilovolts it looks like this, and looking at 20 kilovolts we have a much deeper penetration of the beam into the sample, so we notice a lot of items that are not visible in the lower acceleration voltage. First we had loaded the data and looked at the hardness values and also placed this as a map, and we noticed some artifacts here, and then we wanted to separate the two phases. So the simplest thing that we could do was to place a cut of 5. Now we had this phase and everything else, the white part goes to the other phase, and we saw that we end up with those two values. Now we want to be a bit more advanced. The approach works, but we need to determine the threshold ourselves. So that was quite easy. If we go back to the plot here, we can see that, well, 5 is a good enough choice, but we want to use a machine learning algorithm to make the better choice for us. So let's do this. We take now a clustering algorithm, and the simplest one is to use the k-means algorithm. Maybe it's a good opportunity here for you to stop this video and familiarize with k-means again if you haven't used it in a while. And we know that we have two phases, so we choose two clusters. So we initialize the code and instantiate it inside of that class with two clusters and say that we want to cluster on the hardness value. And then we want to predict what is the best cluster split. So if we do that, that comes out pretty much the same as we would have done naturally. So we have one cluster going up to about 5 and one cluster from 5 onwards. So we can do this again. Now we have two clusters, and this is essentially the same picture that we have obtained beforehand. The problem still is that we have two clusters. So we have this phase and the other phase that we already know. And remember from looking at the electron microscope image that we have a lot of artifacts. Those need to be considered as well. Also, we have to know the number of clusters beforehand. So this is a problem in the sense that we know that we have two phases, but we have all these artifacts, and this sort of muddles the number of clusters we can have. So what we could do is to say, well, we could have 3 clusters, for example. One for martensite, one for ferrite, and one for artifacts. And then we have 3 clusters. If we do that, and we find that doesn't work quite so well, because we still have sort of the structure, but cluster 1 is now everything in black. Cluster the red one, is sort of half of one phase, and 2, the white bit is sort of intermixed between the two of them. Whereas what we wanted to have these bands from one phase, and then the artifacts, and then the softer ferrite phase in between. But this is not what has happened. So why is that the case? Well, we have sort of violated one of the basic assumptions. The small black areas are much smaller than all the other areas, and the hardness value is much lower than the ferrite phase, but there is no distinct peak that the clustering algorithm can use. It sort of tapers off. And therefore we'll need a different approach to prove the analysis. The simplest approach is to use the threshold again. Based on the heat map, we could say, well, everything a hardness smaller than 2 is filtered out, and we use then the clustering approach on the rest. So we could do this, for example, and say, what does the distribution of nanoindentation points look like if we have a hardness smaller than 2, and that we can see, a lot of these artifacts that we want to capture do indeed show up. So this is a sensible approach if you want to do this manually. You can put this now into a new data frame and only put the martensite phase in it. Right? So we have the prediction from it and the hardness, and do this manual filtering. And if we do that before, it looks already a bit better. And we have the martensite islands and not our artifacts. Now what would be nice is to understand how does the hardness vary across the various martensite islands. So think about it, how you can approach this problem. For example, we want to analyze if martensite is always martensite. could be that this area of the sample has slightly different values than this. For example, we want to test this hypothesis if indeed the hardness is roughly uniform across our sample. Now that you've discussed how you could do this, one idea is, instead of using the k-means algorithm, we use a different approach. Most clustering algorithms assume that we know the number of clusters. This is what we had seen in the application of the k-means algorithm that we had done earlier. We had originally 2, and then it didn't work so well for the 3 classes. Right? But here we don't know how many classes we have. Of course, with this given picture, we could sort of count this. But also there's the other assumption that these clusters should be fairly spherical, and while this might be the case here, these islands clearly are not spherical. So we need a different clustering algorithm, and one approach is to use the density-based spatial clustering with noise or dbScan. If you haven't used dbScan for a while, again, it's a good idea to pause this video here and look into dbScan. The main parameters that we need to adjust for this algorithm is the maximum distance, epsilon, between the 2 samples for consideration of the local neighborhood and the minimum number of samples or points in the vicinity of core points. So here we have now a small data frame where we just use the x and y values and then initialize our clustering algorithm. Notice that we only specify the minimum samples and epsilon here and not the number of clusters. We can retrieve all the labels and then see how many clusters we have and add this to our data frame so that each point gets now another column that describes which cluster this particular point belongs to. And once we have done this, we can plot all the clusters that we have found, and we can see that, for example, this large area is one cluster and we have a number of a lot smaller clusters around it. Each cluster gets their unique color. Now we can look at the hardness of all of those 25 values. Now, this is what we had with the manual threshold, right? And this is what we did with the k-means, with the 2 clusters. And now we want to do this for all of those clusters that we have introduced here. So we take our data frame, and in dbScan, the cluster ID -1 means noise, so we take everything that is not noise, and then take the mean and standard deviation of all of those. That gives us another data frame of the 25 clusters, each with their hardness value and standard deviation, and you can see that varies a bit. But we also have large uncertainties, some larger than others, so we put this into a plot, and then we can see, well, they all scatter around. Now, if you combine the measurements into one number, we need to remember that each of these clusters have an associated uncertainty that we need to take into account. We assume now that the measurement of each clusters are independent, and before you do this, discuss this assumption and what that means. So if we combine all of those, we would sort of expect that we get the number that we had before. And you see that if we do that, it's not quite the same. Right? So if we do that, you have the hardness from k-means and the hardness from the manual threshold. And indeed, the central value is fairly similar, although not quite the same, but the uncertainties are much lower. And of course, we have been slightly optimistic with our assumption. Right? So the above procedure means that each of these points are indeed statistically independent, whereas that's not quite the case, because if we scroll back, we can see that, well, this cluster is certainly not completely independent from this one because they're very close together. And so this is why our choice of treating them as very independent has been a bit optimistic. Still, we can see that there is no big issue. They scatter around a certain central value. There are some outliers that also reflect the number